Hi, my name is Travis Berger, and I'm a graduate student at the Institute for Astronomy at the University of Hawaii at Manoa. Today, I will be speaking about my recent work and paper, accepted for publication in APJ, identifying young Kepler planet host stars from Keck-HIRES spectra of lithium with collaborators Andrew Howard and Ann Bosgaard. The goal of this investigation was to use an age indicator, lithium in this case, to differentiate between old and young Kepler systems that were observed in the California Kepler survey, which was detailed in Berger et al. 2017. Unfortunately, stellar ages are frequently unknown or poorly determined. However, determining stellar ages is very important when we consider the dynamic nature of exoplanetary systems. Processes such as planet migration, planet ejection, photoevaporation of planet atmospheres, and planet cooling and contraction from heat from formation likely all sculpt the exoplanet population that we observe today. Unfortunately, these processes do not act on human timescales and instead take millions of years to affect planetary systems. Therefore, we must consider large populations of exoplanets to observe correlations and properties if we ever want to find evidence for the physical mechanisms we believe mold the observed exoplanet population. Although there are a variety of stellar age determination methods, I chose the lithium doublet because it is included in all of my high-res spectra, some examples of which are shown in Figure 3 of our paper, and it serves as a good example of relative age for ensembles of stars. Lithium is a good indicator of relative age because it is burned when it reaches temperatures greater than about 2.5 million Kelvin. Most stars have effective surface temperatures much less than that, so convection is required to push lithium to depths in the stellar interiors hot enough to burn lithium. Hence, cooler stars, which have deeper convective envelopes, burn lithium more quickly than the hotter stars, which have more shallow convective envelopes. To measure the lithium abundance for each of these stars, I created an automated pipeline that measured the lithium equivalent width and then used a combination of Mark's model atmospheres and MOOG to determine lithium abundances for all 1,300 stars in my sample. The result is Figure 7 in our paper, a lithium abundance versus effective temperature plot. Here, the Kepler planet host stars are the red circles, with upper limits represented as downward arrows. In blue is the Hyades curve from Bosgaard et al. 2016. Notice how the empirical Hyades curve, which represents an age of approximately 650 million years old, changes with effective temperature. Like I said earlier, we expect cooler stars to deplete their surface lithium abundances more quickly than the warmer, more massive main sequence stars. We see this in the Hyades curve as we go from 6,000 Kelvin to cooler effective temperatures. So on this plot, we expect individual stars to evolve from top to bottom during their main sequence lifetimes, with cooler stars depleting their surface lithium abundances more quickly. We can also use this plot to compare the ages of these stars, and the blue curve serves as a nice separator of old and young stars, at least relative to the age of the Hyades. Next, we can color the points according to their exoplanet properties, as shown in Figure 10 from our paper. We looked at a variety of exoplanet properties by comparing points above and below the Hyades curve and looking for apparent differences between the two populations. When we looked at exoplanet radius, Figure 11 in our paper, we saw an interesting difference. The systems above, or those that are younger than the Hyades in this plot, appeared to host larger exoplanets. We can display this information in a more quantitative way by plotting the distributions of both old and young exoplanet radii in the purple and green histograms respectively in Figure 13 of our paper. As we can see from this plot, the green histogram appears to be shifted to larger planet radii as compared to the purple histogram. After performing a KS test comparing the two distributions, we find that they are different with a confidence of greater than 3 sigma. Our results suggest that young exoplanets are both different and systematically larger than old exoplanets, which agrees quite well with current exoplanet evolution theories. Photoevaporation of exoplanet atmospheres and contraction from heat from formation are two likely mechanisms to cause this difference between the young and old exoplanet populations. Ultimately, this result is promising, and I hope to investigate it in future studies. If you'd like to know more about our work, please see our paper at the link provided in the description. Thank you for your time.